Hello, good morning everyone. I am myself K. Narsimurthy. I am presently working as an assistant professor in Government First Grade Women's College, Tumkur. The subject which I am teaching is physics, and this is the 43rd video for the second semester students of Tumkur University. I have been presented 42 videos so far, and that covers almost 50% of the syllabus and a new chapter which is magnetic materials, which I started from 31st session, and after that I started a Maxwell's equation. So Maxwell's derived four set of equations. They are as important as the Newton's laws in the mechanics. These four set of Maxwell's equations are the modified form of the laws, means the Biot-Savart's law, Faraday's law, Ampere's law, and the Gauss law. These famous four laws has been modified into four set of equations, and these four set of equations are called Maxwell's equations. The behavior of electric and magnetic field is governed by these four set of Maxwell's equations. Right. Now today I am going to see the Pointing Theorem statement, and I am as well as proving this theorem, and I am looking for what is actually the Pointing vector is. Right. So this Pointing Theorem says that the work done by electromagnetic force on the charge is equal to decrease in the energy stored in the field. So charge is now placed in an electromagnetic field. So force is acting on the charge. What force is acting? Electromagnetic force is acting on the charge. So work is done by the electromagnetic force. If force acts, definitely there will be a work done. Work is done by electromagnetic force on this charge, and that is equal to decrease of energy stored in the electromagnetic field. Okay, so work done is equal to decrease of energy stored in the electromagnetic field, means the work done by this electromagnetic field is at the expense of its energy stored in the field. It has done the work at the expense of the energy stored in the field. Okay, so which is doing the work here? Work is done by electromagnetic force. On which particle it is doing the work? On the charge it is doing the work. So work done on this charge by this electromagnetic force is equal to the decrease in the energy stored in the field. It's kind of law of conservation of energy, means so you need to have some energy, you need to spend some energy for doing the work. So therefore that energy will be decreased in the field. Okay, so work done is equal to decrease in the energy. So what is doing the work? Electromagnetic force is doing the work. This is doing the work on the charge. So at the expense of energy stored in the electromagnetic field, definitely the energy which is stored in the electric and magnetic fields will decrease. If we do the work, the energy will decrease. Okay, so work done by electromagnetic force on the charge is equal to the decrease in the energy stored in the electromagnetic field. Okay, or you can state this Pointing theorem in another way. The decrease in the energy stored in the field is equal to energy which flows out of a surface enclosing the volume. Okay, so whatever the energy, if you take a surface which is enclosing a volume, let us take this surface, spherical surface, and this encloses some volume. So suppose the energy, we have a field inside this volume, we have a field inside this surface, electric and magnetic field. The decrease in the energy of these fields is what actually flowing out of the surface, is the energy that flowing out of the surface, obviously. Okay, so decrease in the energy of the field is what actually equal to the energy flowing out of the surface enclosing the volume V. Okay, right. So either way you can tell this Pointing theorem. Now I am going to derive this Pointing theorem. Now, so let us consider a homogeneous isotropic medium which is free from the charges. and the current. So now the medium which I am considered is absolutely free from charges. There are no charges at all in the medium which I have considered. If there are no charges means there is no question of the current itself. Okay, there is no current in that medium the which I have considered. It is a homogeneous isotropic medium which is completely free from the charges and no current. Now if I write a Maxwell's equation for this free from the charges, the Maxwell's equations will be, so divergence of D is equal to 0 or divergence of E is equal to 0. Second equation I can write it as divergence of B is equal to 0 or divergence of H is equal to 0. Next, third equation is curl of E is equal to minus dou B by dou T, which on substituting for the value of B, it becomes equal to minus mu naught dou H by dou T. That's equation number 3. Now, the fourth Maxwell equation is curl of H is equal to dou D by dou T on substituting D, and that will be equal to epsilon naught dou E by dou T. Okay, right. These are the four set of Maxwell's equation. I have been writing in all the derivations after the derivation of Maxwell's equation. I have written these four set of Maxwell's equation while deriving a velocity of the electromagnetic wave. Now here also I am after that I have written again these four set of Maxwell's equation while proving that the electromagnetic wave is transverse in nature. Now here also while proving this Pointing theorem, again I am taken the four set of Maxwell's equations. Students, for all these three derivations, one is derivations of velocity of electromagnetic wave, second one is to prove that electromagnetic wave is transverse in nature, and third is to prove a Pointing theorem. For all these you need four Maxwell's equation. So that is why I am insisting you to just remember all the four Maxwell's equation. You need to compulsorily remember these four set of Maxwell's equation to do all these three derivations. Right. So I have presented all the four Maxwell's equation. Now let us move further. So taking dot product on both sides of equation 3 with H and equation 4 with E. Now what I am doing is I am taking the dot product of H in equation 4 on both sides. Sorry, equation 3. I am taking dot product of E in equation 4, okay, on both sides. So now the equation 3 becomes H dot curl of E is equal to minus H mu naught dou E by dou T. So I got an equation 5 by taking dot product on both sides of equation 3 with H. Now I'll take dot product with E in the equation 4. Okay, right, on both sides, of course, on both sides. So it is E dot curl of H is equal to E epsilon naught dou E by dou T, and which I am calling it as equation 6. After taking dot product on the equation 3 and 4 with H and E respectively, I got this equation 5 and equation 6. Now let me move further. Now I will subtract equation 5 and 6. Subtract equation 5 from equation 6. Now what is exactly the equation 6? It is E curl of H minus H curl of E. So equation 6 minus equation 5. So E dot curl of H minus H dot curl of E is equal to E epsilon naught dou E by dou T, and minus of minus plus H mu naught dou H by dou T. This is what equation which I got after doing subtraction of equation 5 from equation number 6. I'll get equation number 7. Okay, this I am calling it as equation number 7. Now I will use one vector identity here. What actually this vector identity is? The divergence of A cross B can be written as B dot curl of A minus A dot curl of B. So this particular identity I am using in equation 7. So if I apply this here, E dot curl of H minus H dot curl of E in the left hand side can be written as, so divergence of E cross H according to this identity. I am getting the right hand side of the identity, so I can write this left hand side of the identity there. Okay, so I can write that left hand side of my equation 7, I can write it as divergence dot A cross B. It is div dot A cross B is what actually in the left hand side of equation 7. So div dot H cross E is equal to E epsilon naught dou E by dou T plus H mu naught dou H by dou T. Right, so very simple thing which I am doing here is this curl divergence dot of H cross B, H cross E, I am writing it as divergence of E cross H. So only thing I am changing between these two equations is H cross E, I am writing it as E cross H. So for that you need to add the negative sign, because there is an identity which says that divergence of A cross B is equal to minus of divergence of B cross A. Okay, you cannot simply write A cross B is equal to B cross A, you have to add negative sign. Okay, so divergence of H cross E is minus divergence of E cross H. So I will get this divergence of E cross H as minus of this, minus of epsilon naught E dou E by dou T plus mu naught H dou H by dou T. Let me call it as equation 1, A8, equation 8. Now let us move further. Okay, alright. Now I am doing a very small trick here. What is the trick is, I am doing a differentiation, partial differentiation of E dot E with respect to time. Let's see what I will get from this. Okay, so dou by dou T of E dot E, I have to differentiate this E dot E. So it is E dou E by dou T plus again E dou E by dou T. It's first term into differentiation of second plus second term into differentiation of first. First, it is a differentiation by product rule. Now look at the right hand side of that equation. It is E dou E by dou T plus again E dou E by dou T. It is 2 times E dou E by dou T. So in the next equation I am writing this as dou by dou T of E square. How I got E square? It is E dot E, which is E square. How can you write E dot E as E square? Because there is an identity here which I have written below. Okay, so E dot E, when you are doing a dot product, it is modulus of one vector into modulus of other vector and the cos of the angle between them. So modulus of E and again modulus of E and cos of the angle between the vectors are 0. Now how can you judge that the angle between them is 0? Because they are the same vectors. E and E both are same vectors. If you look at the angle, it will be 0. So angle between the same vectors is 0. So cos 0 is 1. So modulus of E into modulus of E will be E square. So E dot E can be written as E square according to this identity. Now I will write this as dou by dou T of E square is equal to, right hand side is 2 times E into dou E by dou T. I will make a simple rearrangement here. So left hand side I will take E, it is E into dou E by dou T. I will take this entire thing to the left hand side, I will send 2 to the right hand denominator. So it becomes E into dou E by dou T is equal to half into dou square E by dou T, dou square E by dou T. Right, that is equation number 9. Now similarly I can write it for a magnetic field as well. the same thing I will apply for the magnetic field. I will not going to derive that again, because whatever I have derived, I did it for an electric field. Okay. Similarly, I am applying this for a magnetic field as well. So it is h of dou h by dou t is equal to half of dou h square by dou t. Let us call it as equation 10. So equation 10 is this thing for electric field, and equation 9 is for the magnetic for the electric field, and this is for the magnetic field. Now what I am doing is I am substituting both equation 9 and equation 10 in the equation 8. Go back and see what is equation 8. Yes. So it is divergence of E cross H. So in that equation I am substituting equation 9 and 10 in the right hand side of that equation, and if I substitute that, it is minus of half of epsilon naught dou E square by dou t plus half of mu naught dou h square by dou t. There in the right hand side, for h dou h by dou t, I have substituted half dou h square by dou t. Again for E dou h by dou t, I have substituted half dou E square by dou t, first term, right hand side. Alright, after substituting, what I am doing is I am taking dou by dou t outside the bracket. I am writing dou by dou t outside the bracket. You can do that. You can easily do that, because epsilon naught is a constant, mu naught is a constant, half is a constant. So all are constant here except this E square and h square. Therefore, I can write this dou by dou t outside. Okay. So it's minus of dou by dou t half epsilon naught E square plus half mu naught h square. Alright. Let's integrate this over a volume. So I'm integrating the same equations which I got in the previous slide over a volume V. So integration over a volume V, divergence of E cross H into dV is equal to minus dou by dou t integral of volume V half epsilon naught E square plus half mu naught h square into dV. Now by Gauss divergence theorem will simply convert a surface integral into volume integral. Surface integral of a vector is equal to divergence of volume integral of divergence of the same vector. So I have volume integral of divergence of E cross B can be written as surface integral of, now divergence has to be removed, so surface integral of E cross H into ds. That is equal to minus dou by dou t of volume integral of half epsilon naught E square plus half mu naught h square into dV. Now this proves the Pointing theorem. So this equation proves the Pointing theorem. The right hand side of the equation is what the energy rate of decrease of energy with time in both electric and magnetic field. Okay, it's minus and dou by dou t. Minus dou by dou t means it's a decrease. Minus means a decrease. Decrease of rate of decrease of the energy with time, of course. So rate of decrease of energy both in electric and magnetic field. Left hand side is the flux. Left hand side is the flux of electric and magnetic field over a surfaces enclosing the volume V at per unit time. So this is the flux which is going out of the surface S. Okay, so this flux which is going out of the surface is equal to rate of decrease of energy by both electric and magnetic field, the stored energy in electric and magnetic field. Okay, so the rate of decrease of stored energy in electric and magnetic field is same as that the flux which is leaving the surface, S enclosing the volume V is equal to the rate of decrease of energy stored in electric and magnetic field. So this proves the Pointing theorem. Okay, fine. Now we'll see what is actually this Pointing vector is. The energy transported per unit time per unit area by the field is what represented by a vector which is called Pointing vector. Now Pointing vector is actually the energy. What energy it is? Energy transported per unit time per unit area by the fields. Now fields are transferring energy. Fields are transporting energy. Look at the energy which is transported in a unit time, in a unit area. And that energy transported is what our Pointing vector. Okay. So Pointing vector is basically an energy which is transported per unit time, per unit area by these electromagnetic fields. Okay, right, it is represented by the symbol S. Pointing vector is represented by S, which is equal to E cross H. S is equal to E cross H. If I substitute B as mu naught H, that means to say H is equal to B by mu naught. If I substitute in the Pointing vector equation, so our Pointing vector S is equal to 1 over mu naught times E cross B. Okay, right. Alright, we'll move further. I'll make some simplification and finally I'll get an equation for the Pointing vector. So the magnitude of Pointing vector is what actually I'm looking for. Okay, so I know what the direction is. It is perpendicular to both the fields. I know that. But what I'm looking is I'm looking for the magnitude of the Pointing vector. So it is 1 by mu naught E cross B. I know this C is E by B, which gives that B is E by C. So I can substitute B as E by C. So if I substitute in that equation E cross B, instead of B I am substituting E by C. So it becomes E cross E. I told you E cross E is the E square. So it is E square by C. 1 over mu naught E square by C. Okay, so I have substituted B as E by C. So it is 1 by mu naught E square by C. Okay, alright. So S is equal to E square by mu naught C. I am multiplying and dividing this by epsilon naught. So if I do that, it becomes epsilon naught E square by C into 1 by mu naught C naught. Why I have divided and multiplied by epsilon naught is I want something like 1 by mu naught epsilon naught. So I know what exactly this quantity is. The 1 by mu naught epsilon naught is what can be written as C square. Because I know the C is equal to 1 by root of mu naught epsilon naught. Therefore C square will be 1 by mu naught epsilon naught. So I can write 1 by mu naught epsilon naught as C square. Now C square will comes in the numerator. 1C will cancel with the denominator C. So I have left with C epsilon naught E square. So the magnitude of the Pointing vector, the magnitude of energy which is transported per unit area per unit time by these electromagnetic fields is equal to C epsilon naught E square. This is what actually the energy transported. This is what actually the magnitude of Pointing vector. Yeah, okay. So I have given you the definition of Pointing vector. What actually the Pointing vector is? It is the energy, that means it is the energy transported per unit time per unit area by these electromagnetic fields. And I've given a very basic equation of Pointing vector, which is S equals to E cross B. And I tried to see the magnitude of this Pointing vector. I just substituted a very simple things. And I finally got the Pointing vector as S is equal to C epsilon naught E square. But these equations, students, you need to remember all these set of equations, because while solving a numerical problems, you need to remember all these small equations. Okay, so for that you need to remember all this. So I have derived a very important theorem today, which is the Pointing theorem. Very simple theorem, simple mathematical steps are involved. You practice it, you will understand things. I have done the pointing theorem, very important theorem for exam, and I defined what is actually the pointing vector is, and I tried to find the magnitude of magnitude of pointing vector, and I got an equation for the pointing vector as S is equal to C epsilon naught E square. Right. Yeah, these are some of the books which I have referred. You get lot of books with respect to electromagnetism. You go through any books, any good books is okay. So these are some of the books which I refer for this. Okay. Thank you very much.